Professor Sushmita Venugopalan. She is a faculty in Institute of Mathematical Sciences, Chennai, and her area of expertise is symplectic geometry. She will talk about pseudoholomorphic curves in symplectic geometry. Thank you. So I request Sushmita to start.
Thanks for the invitation. Hello, everybody. So to ensure a better quality of the internet, maybe I will turn off my own video and just keep the screen share on. So let me figure out how to do that. Okay, so this talk is going to be fairly elementary, and it doesn't assume that you've seen a lot of symplectic geometry before. So pseudoholomorphic curves are like a big topic of research in symplectic geometry. In fact, they are important tools. And in this talk, in very broad strokes, I want to show you why these are useful objects in studying symplectic manifolds. So let me start by telling you what a symplectic form is. So I assume you know a smooth manifold is. So we start with a smooth manifold M. And a symplectic form is a two form, which is non-degenerate. In other words, what that means is that on every tangent space of this manifold, we have a bilinear skew-symmetric non-degenerate pairing. So omega at any point of M is this kind of a pairing on the tangent space. And by definition of a symplectic form on a vector space, we can deduce that the vector space which has a symplectic form has bases are even dimensional. So therefore, symplectic manifolds are even dimensional. And if you think about it geometrically, the picture for a two form is it can take as input a surface embedded or immersed in your manifold and outputs its area. So I call it an omega area because it's not any kind of honest area, as you will see. So if you have a surface, you can integrate a two form over the surface and you get a number. So the most basic standard example of a symplectic manifold is even dimensional Euclidean space, so R to the 2n, and the symplectic form on R to the 2n is what's written on the slide, summation of dxi, which dyi summed over all i's. So I'm assuming that the coordinates in R2n are x1 through xn and y1 through yn. And if you want to understand how the symplectic form computes the omega area, what it does is, if a two-dimensional surface sitting in R2n, you consider its projections to each of the n2 planes. That means the x1, y1 plane, x2, y2 plane, and so on. And on each of these projections, you calculate the honest Euclidean area. And you add these up, and what you get is going to be the omega area. So that's what the second point here says. The omega area is the sum of n areas, AIs, where AI is the area of the projection of S to the xi, yi plane. And some common examples of symplectic manifolds are cotangent bundles. So in a cotangent bundle, so in R2n, we saw that we pair an xi with an yi. In a cotangent bundle, we, if you consider a coordinate chart, going from x1 through xn, then the xi direction would be paired with the corresponding cotangent fiber direction. And complex projective spaces, they have something called the Fubini study form, which is compatible with the complex structure, and therefore the symplectic form is also called a Kähler form. And as a result, what happens is, since you have this kind of a symplectic form on Pn, if you take any complex submanifold of Pn, the symplectic form restricts to symplectic forms on these smaller submanifolds also. So therefore, any non-singular projective variety is also a symplectic manifold. And some other examples, particular examples, which we are going to see in this talk are, first is the torus. So we already saw the example of R to N. And if you recall, the form we took on it is translation invariant. So in particular, we can translate by the integer, any point in the integer lattice. And and the form remains invariant. So therefore, the form on R2n descends to a form on the quotient R2n mod Z2n. And another example which we are going to see is the two-sphere. And let me point it out here that the symplectic form being a true form on two-dimensional manifolds, it just amounts to giving an area form or a volume form. And so in S2, a symplectic form is just a non-vanishing area form, nothing else. And one of the first theorems you learn in symplectic geometry is that the neighborhood of any point looks exactly like any other point. So the only, for a manifold in the same dimension. So dimension is the only local invariant in a symplectic manifold. So in particular, if you're given a point in a 2n dimensional symplectic manifold, a neighborhood in the, of that point is looks exactly like R2n with the standard symplectic form. So this is called the Gabor's theorem. And this is in contrast with Riemannian manifolds. So Riemannian manifolds are manifolds which are equipped with a metric at every point. So rather a metric on the tangent space of any point. So therefore, on a Riemannian manifold, one can measure things like length, angle, surface area, and volume. And in particular, at any point, one can associate a curvature of the manifold. And so that is a pointwise invariant, and that is something that is absent in symplectic geometry. And this is kind of brought out by this picture over here. So this green ball, I'm thinking of it as S2 embedded in the Euclidean 3 space R3. So both these balls, the ordinary ball and the squished ball on the right, they inherit an area form and a Riemannian metric from the ambient Euclidean space. But these two balls are the same if you think of it as a symplectic manifold. So you can basically construct an isomorphism between these two balls, which preserves the symplectic form. But it's easily seen that they are not the same as Riemannian manifolds. So for example, there are points on the right side ball which have negative curvature, whereas in the left side ball, all points have a positive curvature. So you can't give a map from the left to the right, which preserves a Riemannian metric. So yeah, so inadvertently, when I was talking about it, when I said two symplectic manifolds are the same, there is a notion of isomorphism that we are using in this category of symplectic manifolds. And that isomorphism is called a symplectomorphism. And it's a diffeomorphism between two symplectic manifolds, which preserves the symplectic form. So in particular, if you were to think of R2N, it's an invertible map which preserves the symplectic area. And what it does to any surface, if you were to take any surface in R2N and you apply a symplectomorphism to it, it keeps the omega area unchanged. And some examples of symplectomorphisms in R2N are as follows. So in the first example over here, we are multiplying the first coordinate by 2 and multiplying the conjugate coordinate by half. So therefore, when we evaluate the form on it, it remains unchanged. And in the next example, I'm taking a pair of conjugate coordinates P1 and Q1 and switching it with another pair of conjugate coordinates Q2 and P2. And again, that's a transformation that leaves the symplectic area unchanged. So, so one may ask the question that do symplectic manifolds have any invariants? So for example, Riemannian manifolds had this pointwise curvature as an invariant, but how do you, is there some property of a symplectic manifold which is preserved by symplectomorphism and can possibly be used to distinguish one manifold from the other? So one obvious invariant is volume, because omega is a non-degenerate two form. If you take the wedge of it as many times as the dimension of the manifold, sorry, half the dimension of the manifold. So if it's a 2n dimensional manifold, if you were to take wedge of it n times, it gives you a non-vanishing volume form. So one thing you can do on a symplectic manifold is you can calculate volume. So if you were to, the green ball that you saw, if you were to take a much larger ball with a larger area, then that's a different symplectic manifold. And the question about, so what we saw earlier with the green ball can be thought of as some kind of flexibility in, for symplectic manifolds. And now we want to ask ourselves, is there any structure? Like we just said, we don't have as much structure as Riemannian manifolds, but is there much structure at all? So one of the questions which captures this quality that I'm talking about is that, is a symplectic structure much stronger than a volume form? Is there are there more refined invariants than just the volume form? So another version of the rigidity question is that can any volume preserving map be approximated by symplectomorphisms? Because if any volume, if this is true, then that really shows that there is not much there going on in symplectic manifolds besides the volume form. And the answer to this question is no, as is captured by this theorem proved by Gromov in 1985. It's a very classic theorem. You know, if you were to attend an introductory talk in symplectic geometry, this is just going to be there. And so what this theorem says is that a unit ball in the symplectic vector space cannot be mapped by a symplectomorphism into a cylinder whose radius is smaller than 1. So here I write into any cylinder B2R cross R2n minus 2. So I take two of the conjugate directions, and there I reduce the radius to just R, which is smaller than 1. If I do that, then I cannot embed the unit ball into this thin cylinder. Sorry, I wanted to show you a picture, so let me just jump ahead a little where there is a picture. So something like this. So this is the picture I'm talking about. If this green circle has radius R, which is smaller than 1, then you cannot have an embedding like this, which preserves the symplectic form. So that's what Gromov's theorem says. Okay, and another uh, way of saying this is that a symplectic camel cannot pass through the eye of a needle. So if was a camel which only has a volume form, not a symplectic form, then you can, squeeze it and transform it through volume preserving diffeomorphisms, and it can go through shapes which can pass through the eye of the needle. But with the symplectic form, Gromov's theorem says that you cannot do this. Okay, so in the rest of the talk, I'm actually going to give an outline of the proof of Gromov's theorem. And the proof uses pseudoholomorphic curves, which are an essential tool to capture whatever rigidity is there in symplectic manifolds. So in order to define these pseudoholomorphic curves, I need an analog of a complex structure on a symplectic manifold. So that's what I'm going to define next. So I start out with telling you what's a complex structure on a vector space. So let's consider a real vector space. So a complex structure on a real vector space is just a rule which tells you how to multiply by I. So, if you're on a real vector space, you don't have this multiplication by I operation. So this is just a choice of the multiplication by I operation. And this multiplication by I has to be chosen so that I squares to -1. So that's what's captured in the next line. So J is multiplication by I, and it has to satisfy J square equals minus identity. And further, we want the complex structure J to be compatible with the symplectic form which the vector space has. And compatibility means the following two conditions. So if omega acts on V comma JV, the answer is positive for any non-zero vector. Second is omega is J invariant. So if you can pull out J from both the inputs and the omega value remains the same. So that's what it means for the complex structure to be compatible with the symplectic form on a vector space. So the next step is to move from a vector space to a manifold, which before we do that, I want to point out that what this kind of J does is if you put the omega and J together, we get a pairing on the vector space, which is a positive definite in a product. And the easiest example and the standard example that you should have in mind is that of a complex structure on R2n with the standard symplectic form. So recall that the standard symplectic form pairs dxi and dyi. So there, the standard complex structure takes xi to yi and yi to minus xi. And with this choice of standard J, you can see that the tameness condition is satisfied. That is, if you take the input partial xi comma J naught partial xi and you act upon it with omega naught, that changes to omega naught applied on partial xi comma partial yi, and that's positive. And now let's take this leap from a vector space to a manifold. And what does a manifold have? It has a tangent space at every point. And the tangent space is the vector space with the symplectic pairing. So, and the tangent space is to be thought of as a real vector space. So then what we do is assign a complex structure on every tangent space, which varies smoothly with the point of the manifold. So on a symplectic manifold M omega, an almost complex structure consists of a compatible complex structure Jx on every tangent space, where x is a point on the manifold. So, and compatibility is something you can ensure point-wise. Yes, and what happens all of a sudden is you started out with a symplectic manifold which didn't have any local invariants. And if you choose a J, then suddenly your manifold becomes a Riemannian manifold, because omega and J taken together form a Riemannian metric. As we pointed out earlier in the case of vector spaces, so this is the pairing we are talking about. V comma W is mapped to omega of V comma J W. So you can do this at every point on a manifold. So you get a positive non-degenerate pairing of the tangent space at any point on the manifold, and that's precisely a Riemannian metric. So what's happened is choosing a J makes a symplectic manifold rigid, because we were earlier saying that Riemannian manifolds are rigid. But wait, there are many choices for a compatible almost complex structure. There's no one unique God-given one. So there are many ways of making the symplectic manifold rigid. But then the space of omega compatible almost complex structures is connected. So if you choose two different ways of making this manifold rigid by choosing two different almost complex structures, J0 and J1, then since the space is connected, you can always connect J0 and J1 by a path of compatible almost complex structures. So which means that what's going on in the manifold with J0 can be maybe smoothly deformed to the manifold with J1. So there is some expectation that this one choice of rigid manifold might be related to this other choice of rigid manifold. So connectedness of the space of compatible almost complex structures implies that certain properties of the rigid space M omega J0 are preserved in M omega J1. So actually, as a side remark, more it can be said about the space of compatible almost complex structures, and that is that the space is contractible. It's not just connected, it's contractible. But that's not relevant for us right now. Any questions? Anybody wants to ask me a question?
So, hello.
Hello?
Yes, I want to ask a question that you are talking about the compatibility of the vector space.
Sorry, can you introduce yourself? I don't know who you are speaking.
I am Ankur, sir.
Sorry?
Ankur.
Ankur.
My name is Ankur.
Okay.
So for compatibility of vector space, you introduced two conditions.
Mm-hmm.
The first, what do you mean by the first condition? And another question is that
we can do one question at a time. 1 second. Let's go there. So the first condition. So the first condition is kind of what guarantees that the pairing is positive. Do you see that? Because in this Riemannian pairing, in the third point, if you take V and W to be equal, so if you take V comma V, so I mean here, okay, here. So if I take V equals W, then what I get on this side is omega applied on V comma JV, and that's positive. So that ensures that this it's a positive pairing. So that's the effect of the first condition.
One more question is that does for all symplectic manifold almost complex structure exist?
Yes, that's right. Yeah.
And another one is that you are taking, basically you are differentiating two almost complex structure by that by the linear map J, right? Means you are saying that two almost complex structure are different if the mapping J which you are taking is different.
Exactly. Yeah. Yeah.
So
J is the almost complex structure.
okay. Thank you.
Yeah. Okay. Any other questions? Okay.
There is a question in the chat box.
I don't chat box. Let's see. Is there any cohomological obstruction on a manifold to have a symplectic and almost complex structure? So as Ankur pointed out, if you have a symplectic structure, almost complex structures are guaranteed to exist. So the question I need to answer is cohomological obstructions for the existence of a symplectic form. So the most obvious restriction is that we want the second cohomology group to be non-zero, because the omega is a closed, oh sorry, this is kind of a typo on the first slide. So omega is not just non-degenerate, it's a closed two form. So it's a representative of an element in the second cohomology group of the manifold. So, so not only you want the second cohomology group to be non-zero, you also want that if you take the cup product of n at the second cohomology group taken n times, which maps to the top cohomology group, that should be non-zero. So those are the obvious cohomological obstructions, but I have a feeling that's probably not enough. In terms of homology, that's enough, but that may not be a sufficient condition. That's my feeling, but I don't have examples off the top of my head. So there's another question in the chat box. What properties are expected to be preserved between compatible almost which are path connected? Yes, I think that's what we are going to talk about in the rest of the talk. I'll try to motivate some such properties which are expected to be preserved between compatible almost complex structures. Any more questions? Okay, so let's move on. So our goal today is to prove Gromov's non-squeezing theorem, and tool we have at our disposal are J holomorphic curves. By that, what I mean is that you would have studied holomorphic maps in your complex analysis class, which means that a map is holomorphic if its derivative is complex linear. So here, we don't have a complex structure on a manifold N, but we do have an almost complex structure. So, it's possible to define a notion of holomorphicity. So I take a little bit of a shortcut and don't define it as a holomorphic curve as a map, but rather just define it as a submanifold sitting inside our symplectic manifold. So if we start with a symplectic manifold with a compatible almost complex structure, I just define my J holomorphic curve to be an immersed submanifold for which the tangent space is J invariant. So for example, if you were to take the, sorry, this should have been clarified here itself, but this is called a curve because it's a complex curve. This immersed submanifold is actually two-dimensional. It has two real dimensions, but it's called curve because it's like a complex curve. And one of the examples you can think of using what the basic examples we have at our disposal, if you look at R2N, so if you look at the two planes spanned by X1 and Y1, that is holomorphic with respect to the standard J0, which we defined in our earlier slides. Okay. So this is kind of a motivational result, which tells you what property is preserved when you go from J0 to J1. So if you have two compatible almost complex structures, what exactly is preserved? So this is kind of a motivational result. It's roughly stated. I don't state a lot of the hypotheses which are required. So suppose J0 is a compatible almost complex structure on a compact symplectic manifold for which there is a fibration. So we are considering a very special situation where M has, so by a fibration, I just mean that pi over here, sorry, I'm not able to highlight it. Pi is a submersion. So which means that all of its fibers are the same, and the fibers are J0 holomorphic curves. Okay, so if you have this kind of a fibration, it's then, so this is a very special situation which is going on here, that the manifold can be fibered by J0 holomorphic curves. So if you can do that under some hypothesis, you can also do it for any other almost complex structure. And I mean the proof for this is involves a lot of machinery, and that's why I don't get into stating all the hypotheses here.
Sorry, Suma here. So is this curve compact? You are taking compact surfaces?
Because so this is a yeah, for our purposes, just think of curves as P1s. In fact,
okay.
They can be compact, but in general, there's nothing in the definition to rule it out. But the basic examples that we encounter, you can just think of these curves as P1s.
Okay, thank you.
So this is kind of the picture. What happens is, in the top, I have tried to draw a manifold fibered by J0 curves. And if you change the J0 to J1, the curves get shifted around a little and looks like the bottom picture. So this is roughly our result is saying that if you have the top picture, then you have the bottom picture for any J1. And what we are looking at here is, one could say the first example of a Gromov-Witten invariant. So Gromov-Witten invariants are like a big thing which are studied by symplectic and algebraic geometers. So we have, in this very simple scenario, we have encountered a Gromov-Witten invariant, namely. What we have shown, we have not shown anything. What happens in this situation is that if you fix a point P, there is one J curve passing through the point P of the homology class as the fibers. So earlier we said that there are these fibers C sub B, right? So for any base point, little b and b, CB is a curve. So if you take the homology class of that fiber and you ask yourself through any point in the manifold, how many curves are there of this homology class which are J holomorphic? And the answer to that question is 1. And that is an invariant of the symplectic manifold. And it's an example of a Gromov-Witten invariant. And in general, Gromov-Witten invariants are counts of curves satisfying, when I say curves, I mean holomorphic curves. So you fix a J and count the J holomorphic curves, satisfying certain constraints. So in this case, the constraint it satisfied was that it should pass through a fixed point P. So in general, your constraint could consist of the curve having to pass through a point or through a cycle, something like that. Yeah, and because of the fact that we have any two almost complex structures can be connected by a path, the Gromov-Witten invariant is supposed to be independent of the choice of J. So whenever it's the invariant is, the theory is properly defined, you'll be able to show that the invariant is independent of the choice of J, and that's proved using the fact that any two J's can be connected by paths of compatible almost complex structures. But yeah, in general, what often happens is that this is what Wikipedia has to say about a Gromov-Witten invariant. So Gromov-Witten invariants are rational numbers that in certain situations count pseudo-holomorphic curves meeting prescribed conditions in a given symplectic manifold. So the point is that it's hard to define these invariants in full generality. So then you have to come up with a theory which extends whatever there are some cases where these invariants can be defined, but you want to extend it to all possible symplectic manifolds, then you have to extend the theory in a consistent way. But in those extensions, it's not even fair to say that they are actually counts of pseudo-holomorphic curves. So that's why they use this language that these invariants are rational numbers. Notice, rational numbers, not integers. That in certain situations count pseudo-holomorphic curves. Okay. Yeah, but those are not the complexities that we are going to talk about today. So I'm kind of the interest in these invariants started out with one of these initial results by Kontsevich, who produced a recursive formula for the number of degree D curves in P2, complex projective space P2, passing through 3D minus 1 fixed generic points. So this number 3D minus 1 is important so that you get isolated curves instead of families so that they can be counted. So that's Gromov-Witten invariant, which Kontsevich computed. Okay, so now let me get back to the proof of Gromov's non-squeezing theorem. So let's before we start proving the result, let's just recall the statement which says that a unit ball in a symplectic space cannot be mapped by a symplectomorphism into a cylinder which is narrower than the ball. In particular, you cannot have this picture if R is less than 1. Okay, so in order to prove it, let's assume the contrapositive and assume that we do have a symplectomorphic embedding from a unit N ball to this thin cylinder. So let's call this F. So in order to be able to apply any of those results from Gromov-Witten theory, we need to be on compact manifolds. So right away we have this problem that the cylinder on the right hand side, the green cylinder, is not compact. So we'll first try to change it to a compact manifold. So what we do is, one of the factors is a 2 ball, and we embed this 2 ball into a 2 sphere. So we need to take in, so remember that a 2 sphere, a symplectic form on a 2 sphere just consists of an area form. And a ball also has a standard area form. So it's not very hard to visualize that you take a ball of slightly larger area, you take a sphere of slightly larger area and embed the ball into it. So you can, in fact, you can assume that your sphere has area pi r plus epsilon square, where epsilon is small enough so that r plus epsilon is smaller than 1. So you take an embedding like that. So now one of the components has been converted to a closed compact manifold, which is this 2 sphere. And now we have this second component, which is R2n minus 2. So what we do with that is we mod out by some multiple of the integer lattice. And by modding out, we get a torus. So we quotient the factor R2n minus 2 by a lattice multiplied by a number A, which is chosen to be large. So we get a 2n minus 2 dimensional torus. So the space we are working with is a 2-sphere times a 2n minus 2 dimensional torus. Okay, and remember that we had embedded our unit 1 ball into the cylinder. So we need to take the A large enough so that this embedding remains an embedding. So that this torus, this part has to be large enough. If you make it small, this embedding will start, the blue will start overlapping with itself, which is not good. So we have converted a non-compact manifold into a compact symplectic manifold. Now let's start staring at this new compact target space that we have created. So we take the easiest possible compatible almost complex structure, which is the product almost complex structure. So that consists of a J on S2 and a J on T2n minus 2. There is a typo over here. Sorry about that. So this is wrong. This should have been 2n minus 2. So this is a product, and put J's on each of them separately. And then if you put it together, you have a J on the total space, which is a product. So if you take this product almost complex structure, what we notice straight away that we have a fibration that we talked about earlier. So this is indeed one of those special cases where the manifold fibers into J curves, where the J is the standard J. So indeed, the fibers of these fibrations are just one of the factors of the product. So one of the factors is an S2. So the product factors and the fibers are S2. So this is a trivial fibration. And the S2s, because of our choice of almost complex structure, are holomorphic under this J standard. So any questions about this picture? Okay. Okay, so now this is kind of the punchline. So that the motivational result, which I stated without proof, which is kind of sweeping under the rug a whole lot of technical machinery, it said that if you have a J holomorphic fibration for one J, then you also have it for any other J. In particular, the chromo invariants are preserved. And what that means is that if I change the J now, so that's what I'm going to do. Instead of the standard J, I'm going to take a non-standard J and use the fibration that I get. So now I'm going to take a new J, which is very non-standard. What that J is that the blue ball over here, the 2n dimensional unit ball, that comes with the standard almost complex structure. I push forward that one, and in the blue region, I get an almost complex structure, which I extend in any arbitrary way over the rest of the green region. So that's a legitimate compatible almost complex structure. And our result said that through any point, there is a J curve, which is homologous to S2. So by our earlier result, for any compatible almost complex structure J, there is a J curve C of homology class S2 cross point through the point FP. And FP, notice what it is. I take P to be the origin of the ball, and FP is the image of the origin. So I take the J curve through the image of the origin. And our machinery tells us that such a curve indeed exists. So let's call, yeah. So let's call this curve through f of t C, and its inverse image is called C prime. Okay, and so now if you look at C prime, it's a J naught holomorphic curve. Note, so this is something we need to notice. The way we constructed the new J was that it is same as J naught in the blue part. So when you pull it back, this red curve is going to be J naught holomorphic in the unit ball. And holomorphic curves have the special property that they are area minimizers for the metric. And in this case, the metric is the standard Euclidean metric. Thus, C prime is the minimal surface in the Euclidean ball. And by the theory of minimal surfaces, the least area surface in the ball, whose boundary lies in the boundary of the ball and which contains the origin, is the flat plane. So basically, the theory of minimal surfaces rules out, things like fingers. If you have a small circle in the boundary, and you cannot have a finger-like object coming and hitting the center of the sphere, because that small circle can just be closed up with a plane there itself. It doesn't have to come all the way to meet P. So if a surface does that, then that is not a minimal surface. So in the Euclidean metric, the minimal surfaces are just planes. So if I tell you that a minimal surface passes through the origin, it necessarily has to have area at least pi. So therefore, the area of C prime has got to be at least pi. But if we recall how we obtain C prime, C prime is homologous to this S2, which has an area of R plus epsilon. So the C cannot have area more than R plus epsilon. Sorry, pi times R plus epsilon square. So, and so therefore we have arrived at a contradiction here. So basically the basic idea is that if a minimal surface has its boundary on the unit sphere, in order to hit the origin, it has to have area at least pi, because that's the minimum you can do with a flat plane. You cannot do better than that. But the holomorphic curve that we constructed has area much less than that, which is not possible. So that basically contradicts the fact that R is smaller than 1. So leading to the proof of the non-squeezing theorem. So I'll stop here and I'll let you ask questions, because we still have some time.
Is there any question?
Hello. This is hello.
Hello.
I'm Manav. Is this audible?
Yeah, it is.
Yeah. So you've said that holomorphic curves are area minimizers for a given metric, right? So
yeah, not for and the metric is given by the omega and j that you are considering.
Yeah. So this is a area minimizer under what class of curves? Like it minimizes.
So actually, if you look at the theory of minimal surfaces, it's kind of a pointwise differential equation that it has to satisfy.
Okay.
So, yeah.
Oh, okay. It comes out as the like minimizing in the sense of the critical point for differential equation, that sort of.
Yeah, it's something like that, right?
Okay.
Yeah.
Okay. Yeah. Okay. Thank you. Yeah.
Any other question? Okay, if there is no other question, let's thank the speaker.